Okay. Group 6 elements of the periodic table, or group 6 derived drugs. Since we have already looked at group 7, the next group we have to know is group 6. So group 6 has its elements, and majorly we are going to look at 2 elements since they are the ones that we are much interested in the field of medicine. We shall look at their elements, their compounds, how they can be prepared, how the different compounds can be made, and then what is their use in the field of medicine. So we start with one element, that's oxygen and its compound. Oxygen is a widespread element in the earth crust, and it constitutes 23% of atmosphere in the free state. We have majorly 3 sources of oxygen. We have water, minerals, and rocks. So we have properties. We need to know the properties of oxygen. Oxygen supports combustion. It supports burning. Oxygen is a colorless gas. It has no smell, so we shall say it is odorless. And then it has no taste, meaning it is tasteless. So how do we prepare oxygen? Oxygen is prepared in 4 main methods. The one being electrolysis method, the second one being cyanogenic separation, and then the third one being the pressure swing absorption method, and then the last method is membrane filter technology. Electrolysis method, oxygen is produced by electrolysis of aqueous solution of acids and alkali. Aqueous solution meaning they have water component in it. So when water completely dissociates, we are going to have hydrogen ions migrating to the cathode, where we gain electrons and then transform into a hydrogen molecule. Then we have the hydroxide ions, or someone can say hydroxyl ions, which become discharged at the anode with the formation of water and oxygen. So water dissociates completely. We have equations of reaction backing up our explanation that we have already talked about. We have water completely dissociating to give us hydrogen ions and hydroxyl ions or hydroxide ions. So we see here this is a plus sign or cut ion because it crosses the 2 lines, and then one line we call it the anion. So the cut moves to the cathode, and then the anion moves to the anode. That is why we see that these hydrogen ions migrated to the cathode, and we expect to see addition of electrons in order to make this a neutral compound. So we get hydrogen gas, and then the hydroxyl ions give us water and oxygen gas, as we can see in that. So that's all about electrolysis. The second method of preparation is cyanogenic separation. Under cyanogenic air separation unit is an old process used to produce high purity oxygen, and a specific percentage, or the percentage of purity, is 99.5%. The 0.5% can be the impurities that can come along with the gas or air. So this specific method, we can either prepare oxygen using this method, or we can also prepare nitrogen using the same method. So this technology is centered on the fact that each of the air's constituents has different boiling points. All the constituents of air, all the components of air they all have different boiling points, be it nitrogen, be it carbon dioxide, be it ammonia, they all have different boiling points. So since we appreciate the difference in boiling points, we are going to separate our oxygen depending on its boiling point. So the process involves lowering the temperature of air such that nitrogen and oxygen separate based on their boiling points. That's all you need to know about the cryogenic separation, separating air depending on their boiling points. The third method of preparation of oxygen, we have the pressure swing adsorption. Pressure swing absorbers are a much newer technology as compared to cyanogenic. Since we said cyanogenic is an old method, we have a new method called pressure swing adsorption. Pressure swing adsorption devices take atmospheric air into a pressurized tank. So we collect air in the atmosphere, we collect the air in space, and then we put it in a pressurized tank containing zeolites. Zeolites under pressure have the ability to deform and create a dipole. So this dipole allows for the collection of nitrogen but allows oxygen to pass. So the main aim of having these zeolites that creates a dipole is to absorb nitrogen. Since nitrogen has a greater percentage of air or consists of a greater percentage of air, there is need for us to separate it out or collect it and allow our oxygen to pass. So here we continue and say after a certain volume of air has been separated, the zeolites will become saturated with nitrogen since they are the ones absorbing nitrogen, since they are the ones collecting nitrogen. By dropping the pressure of the tank back to atmospheric pressure, the zeolite returns to its original polarity, liberating nitrogen. So this method can give us both oxygen and nitrogen. We have membrane technology as another method of preparing oxygen. Conventionally, membrane technology involves passing air over a membrane filter. The filter will allow fast gases to pass and slow gases will stay. Oxygen is considered a fast gas. Nitrogen and argon are considered slow gases. The ion transport membrane technology can produce greater than 99% purity of oxygen. So we see that this method gives us 99%. The cyanogenic method gives us 99.5% purity of oxygen at a much lower cost than cyanogenic. So you may find cyanogenic may need us to inject a lot of money or a lot of time, but with the membrane it gives us at a lower cost. So someone would prefer to use the membrane technology instead. This air is passed over a ceramic membrane made of metals that are oxygen depleted. The membrane accepts the oxygen where it is ionized and diffused through the membrane due to the difference in oxygen partial pressures across the membrane. So we have the ITM oxygen process. So this is like what happens in the membrane technology, the ion transport membrane. This ITM is ion transport membrane. So we see what happens. We see that it is oxygen that is able to pass as other gases stay or continue. So byproducts of oxygen, water electrolysis. is a process by which water is broken into hydrogen and oxygen. So after we have manufactured oxygen, there is need for us to know how we can store it. So equipment used in oxygen service must meet stringent cleaning requirements, and systems must be constructed of materials that have a high ignition temperatures and that are non-reactive with oxygen under the surface conditions. Cyanogenic liquids are liquefied gases that have a normal boiling point below 130 degrees Fahrenheit or 90 degrees, that's 90 degrees Celsius, and then liquid oxygen has a boiling point of 297 degrees Fahrenheit. When translate it to or change it to centigrade, you find that those are 183 degrees centigrade. So we have liquid oxygen, and it is the one that we can easily store. And for it to be liquefied, it has to have this specific boiling point that we have here. We need to know the normal and when it is liquefied or when it is in liquid form. Oxygen is often stored as a liquid. Although it is used primarily as a gas, liquid storage is less bulky and less costly than equivalent capacity of high pressure gaseous storage. A typical storage system consists of a cyanogenic storage tank, one or more vaporized, and a pressure control system. The cyanogenic tank is constructed in principle like a vacuum bottle. There is an inner vessel surrounded by an outer vessel. Between the vessel is an annular space that contains an insulating medium from which all the air has been removed. This space keeps heat away from the liquid oxygen held in the inner vessel. Vaporizers convert the liquid oxygen into the gaseous state. A pressure control manifold then controls the gas pressure that is fed to the process or application. So after you have known how to prepare oxygen, you need to know how to store it. And after you have known how to store, you also need to know the uses. How do we use oxygen? Oxygen is generally liquefied so that it can be more effectively transported and stored in large volumes. Medically, oxygen is used to sustain life. In the metal industries, in conjunction with acetylene and other fuel gases for metal cutting, welding, scarfing, hardening, cleaning, and melting. So these are all points. You can say in the metal industries, we use oxygen for cutting, welding, scarfing, hardening, cleaning, and then melting. Those are 6 points. In case you're asked for more, the 3 uses of oxygen. Oxygen enhances the combustion process in industries that manufacture glass, aluminium, copper, gold, lead, and cement. So this is when we use it in the manufacturing industry or process industry. Here when we use it in the metal industry, and then here when we use it in the field of medicine. So it is used to sustain life. So cases that may be life-threatening and may need oxygen, we have cases of asphyxia. So when your patient presents with asphyxia, there is need for you to give the oxygen to sustain life. Okay, so we need to also know and appreciate that we have compounds or oxygen compounds. We majorly have two compounds of oxygen, that is distilled water and hydrogen peroxide. So here we are starting straight away with the distilled water. Organic potable water contains many organic and inorganic impurities. These impurities include sulfates, nitrates, calcium, and magnesium oxides. However, we need to note that water with impurities cannot be used for preparing medicinal agents, since salts in water may alter or react with pharmaceutical ingredients. Furthermore, organic impurities create favorable conditions for pathogenic microbial growth. Yeah, for pathogenic microbial growth. So for us to make or have water that we shall need to use for preparing or for pharmaceutical preparations, there is need for us to make sure that they are free of organic and inorganic impurities. So we have to make sure that the inorganic impurities like maybe the chlorates, the carboxylic compounds don't have to be in the water, as well as the inorganic, the sulfate, the nitrates, the calcium, and magnesium oxides as well should not be present in our water that is going to be intended for use. That is briefly introduction that we needed to know about water. So when we are asked for impurities of water, we can give a number of impurities that we can get or test for. We have the organic, the inorganic, the sulfates, the carbonates, the chlorides. Those are all the impurities that we can find in water or in our distilled water. And to become some of the quality control tests we have to carry out in order to check whether we have prepared or distilled our water using the right method of distillation. So water has properties, or distilled water has the properties. We see that it is colorless and transparent liquid, it is odorless, it is tasteless, it is neutral, having a pH of 5 to 6.8, that is a neutral pH, or we can also say 6.8 to 7 as the neutral pH, either 2 or 6 to 7 as the neutral pH. That you need to know that and appreciate that water, distilled water, has a neutral pH and then specific gravity of 4 degrees centigrade. The water has a gravity of 4. Specific gravity at 4 degrees centigrade must be 1. So the specific gravity of water is 1 at this specific temperature. And then the boiling point of water at this pressure, that is 760 millimeters per mercury, should be 100 degrees centigrade. So we have storage. Distilled water should be stored in a well-sealed bottle filled up to the top. The stopper should be provided with calcium chloride to be filled with soda lime and cotton wool to prevent carbon monoxide from getting into the container. That is how we need to store it, or what we need to put into consideration to store. So just like how I was saying that distilled water can have impurities, we have to carry out different tests to find out whether our distilled water does not contain impurities. So these are some of the tests that we can carry out, or someone can say the quality control tests that we need to find out or carry out, and they call them identification tests for distilled water. So can be quality control tests. So our identification test, we are generally trying to check out for any impurities that can be in water. So the first thing we have to know is check for the pH. And earlier on we talked of a property of water or distilled water having a pH of 6 to 7 or 6.8 to 7 or 5 to 6.8 being neutral. So here that we have a reagent we use. This reagent is methyl red indicator. When we use methyl red indicator and then we observe a yellow solution, meaning it is neutral. But if we have no observable change, we are going to say that our pH, we shall say that our pH, it may be acidic or basic, and if it is acidic or basic, then it is not distilled water and it will not be ready to be used for preparation or pharmaceutical preparation of medicine. We have tests for salt and mixtures. We also have to check for salts. With the salts, we are going to get a small amount of water and expose it to heat, or we call it evaporating it. We get water, put it in a petri dish or anything that can heat up the water, and then you leave it to evaporate. If by the end of the process and when all the water has been evaporated and there is no water, no salts left on that container you used, that will show that there are no salts. But if there are salts that you are able to see after the water evaporates, it means that it will mean that there are a number of salts in the mixture, and if salts are in the mixture, meaning our water is not ready to be used. So we have the second thing as carbon monoxide. With carbon monoxide, we are going to use a reagent that is lime. This lime is our lime water, or another person can say calcium hydroxide. Observation for this, we are going to see a turbidity confirmed, or a turbid solution formed, or a cloudy solution. When a cloudy solution or a turbid solution is formed, it confirms the presence of carbon monoxide. And then, if there is no change, shall say carbon monoxide absent. So this works for both carbon monoxide and carbon dioxide gas. We use the same reagent as lime water or calcium hydroxide, and if we do not see turbidity, we shall say that they are absent, and we shall recommend their water to be used for pharmaceutical preparation. So that is all about distilled water. We also have other identification tests. For example, for organic compounds, we make sure that we use potassium permanganate. So when we add potassium permanganate to our water and we have no observable change, we shall say that organic compounds are absent. But if the purple solution of potassium permanganate turns to a colorless solution, we shall conclude that organic compounds are present in distilled water. And we said that when organic compounds are present in distilled water, it will breed the microorganisms, and this will bring about microbial instability of whatever product we shall use or make with that specific water that we didn't check for its purity. So other identification tests, we shall share them in class. We look at another compound of oxygen, and that compound is called hydrogen peroxide. So we also need to prepare hydrogen peroxide. Hydrogen peroxide can have a number of ways in which we can prepare them. The first is preparing it from a peroxide itself. And here we prefer to take barium peroxide, that is in the laboratory. So in this method, a hydrated barium peroxide is a peroxide that has water of hydrolyzation. Water of hydrolyzation is when we see this dot between this compound and this. So this is water of hydrogen peroxide. So hydrated barium peroxide is reacted with sulfuric acid to produce barium sulfate, hydrogen peroxide, and water. The peroxide produced is 5% solution. So this is how we can prepare 5% hydrogen peroxide solution. We use a hydrated barium peroxide plus sulfuric acid to give us barium sulfate. This is the chemical structure of barium sulfate, and then hydrogen peroxide and water, as simple as that. Another method we use is electrolytic method, that is still electrolysis. Okay. In this, a 30% ice cold concentrated sulfuric acid is electrolyzed at a high density. Peroxide sulfate is obtained, which is then hydrolyzed to get hydrogen peroxide. So we can also use another peroxide apart from barium peroxide. We can also use sodium peroxide. Sodium peroxide reacts with dilute sulfuric acid, producing hydrogen peroxide and sodium sulfate only. So this is our sodium peroxide reacting with sulfuric acid, giving us sodium sulfate and then hydrogen peroxide. This should have a 2 behind. So this is hydrogen peroxide. We have these compounds being formed. So this is another method. So this is already the third method of preparation. The fourth method we use is electrolysis of acid ammonium sulfate solution. Hydrogen peroxide is produced commercially by electrolysis of acidic ammonium sulfate solution. Cathode. So we find that as the cathode, we expect the ammonium ions discharged at the cathode and forms ammonia gas. 2 ammonium salts residues give up 2 electrons and forms ammonium persulfate. The latter is decomposed with the formation of hydrogen peroxide. That's another method. However, we have properties of hydrogen peroxide. These are majorly the physical properties. You see, it is miscible with the water, it dissolves in water, and then it has a boiling point of 150.2 degrees centigrade, and it is acidic in nature. It is a pale blue liquid. Some books can tell us it is a colorless liquid. So some people see the pale blue as a colorless depending on the site. So whether a person puts a colorless or pale blue, it is as well given a mark. It is more viscous than water. When we look at viscosity, we are looking at the density, the weight of hydrogen peroxide. As in, when we compare the density or the viscosity, it is more viscous than water. And then it is an oxidizing agent as well as reducing agent. It has both oxidizing and reducing properties. That's what we need to appreciate about hydrogen peroxide. Oxidizing properties of hydrogen peroxide. Hydrogen peroxide oxidizing properties are exhibited in reactions with iodides and bromides as well as ion 2 salts. So in this specific case, we are having potassium iodide reacting with hydrogen peroxide and then in the presence of an acid, so you find that this iron is oxidized to this iodine or iodide is oxidized to iodine, and then we find that this water is being reduced, this hydrogen peroxide is being reduced to water. That is why we end up finding iodine, potassium sulfate, and then water. The same comes with the bromide. The bromide is oxidized to bromine, giving us these compounds. We find that potassium bromide with hydrogen peroxide with our sulfuric acid, giving us bromine, potassium sulfate, and water. So it is oxidizing property is also exhibited when we have iron compounds. We find that iron 2 is oxidized to iron 3. So iron 2 reacted with hydrogen peroxide in the presence of an acid is oxidized to iron 3 sulfate and water. So that is the oxidizing property of hydrogen peroxide. So we also talked about the reducing properties. We see that reducing properties of hydrogen peroxide. The reducing properties of hydrogen peroxide is seen in reaction with acidified solutions of potassium permanganate, or we can say acidified potassium permanganate, where a purple solution of potassium permanganate turns to colorless with the vigorous evolution of oxygen gas. This reaction can be used for identification of hydrogen peroxide. So we can identify the presence of hydrogen peroxide using acidified potassium permanganate when we see a purple sorry, excuse me. When we see that a purple solution of potassium permanganate is turned to a colorless solution, we shall conclude that a peroxide is present. Though we have other reagents that we can use to identify the presence or confirm the presence of hydrogen peroxide that we are going to look at in the next slides. So this is the equation of reaction of what happens when we have a potassium permanganate ion reacting with hydrogen peroxide in the presence of an acid. These protons are acids. We get manganese ions, manganese 2 ions, and then water and oxygen gas. So that is the properties, at least the understand the reducing and the oxidizing properties of hydrogen peroxide, because that is what makes hydrogen peroxide unique from other elements. From other elements, or we can say other compounds of the periodic table. Elements, sorry about that, of the periodic table. So let's look at the uses of hydrogen peroxide. Hydrogen peroxide is used as antiseptic. It is also used to arrest bleeding of wounds. That's why we find that at a specific percentage, we have hydrogen peroxide being used for cleaning wounds. So it is used majorly to arrest bleeding. So used as a mouth rinse to help remove mucus from the relief of minor mouth irritations. We have mouthwash. We find that 2% or 3% hydrogen peroxide is used as a mouthwash, and it is used to remove the mucus for the relief of minor mouth irritation. Storage. How can we store hydrogen peroxide? It is stored in an orange bottle with a wax coated or a glass stopper to prevent decomposition by sunlight. So that is all what we needed to know about group 6 elements of the periodic table. However, we have sulfur and its compounds. So I'll ask you to research on sulfur. The main compound of sulfur that we are going to deal with is sodium thiosulfate. So read about sodium thiosulfate and then it is assay and do some research on that. However, thank you for listening. The struggle continues. I wish you all the best. I think R is missing here for the struggle. The struggle continues. I wish you all the best. Thank you for listening.